Okay, so recording has started. Let's begin today's session. So, welcome all. This is our week 10 live interaction session for Aspen Plus simulation software course. It's a basic course for beginners where you get familiarized with the various modules in Aspen Plus and how to do process plant simulation in the Aspen Plus software. Okay, so brief about me. I'm Bhavesh Moorjani. I'm currently pursuing my Ph.D. from IIT Bombay, and I have completed my bachelorates from MS University Vadodara, where I was introduced to Aspen Plus software as my UG curriculum, and right now I'm TA for this course, so that I can help you guys to learn more about Aspen by doing various problem sets in this live interaction session. Okay, so this is the week 10 class, and in today's class we will be looking at different case studies. So I have taken out 4 case studies for today's class. Hopefully we will be able to complete all 4 in today's class. If not, then we will reserve it for the next class. Okay, so there are 2 distillation column example, 1 heat exchanger example, and 1 decanter example. So I think one student in the last class was asking regarding this previous year's assignment, so I have included this also. Okay, so we will move ahead with all the examples. So right now anyone hasn't joined, but then it's fine. Okay, so let's start with the question 1. So this is the example of use of M heat exchanger in the Aspen Plus software. Okay, so what is the problem statement says that we have a natural gas which is coming at 1 kilomole per second flow rate at 25 degrees centigrade and 55 bar, which is to be liquefied to produce LNG. LNG is a liquefied natural gas for transportation purpose. LNG will be cooled to minus 163 degrees centigrade using single stage mixed refrigerant process. So this is a PRICO process. It's a trademark process. The refrigerant is compressed to 39.65 bar and then cooled using a seawater cooler. The refrigerant passes through a heat exchanger where it condenses, expands across Joule-Thomson valve, and then returns to the compressor. Our goal is to find overall heat transfer coefficient, compressor load, generate temperature versus enthalpy composition curve for both cold and hot stream using Peng-Robinson method. So this example that has been taken is from this reference article. This is from Watson et al., which is on modeling and simulation of phase change and non-ideality in multi-stream heat exchanger. So if we will go into this paper and try to find out its content, so they have provided various methods for refrigeration cycle, like liquefaction of the natural gas. I had its PDF ready. Let me quickly check it. So yeah, this one. Just like modeling and simulation, phase change and non-ideality in multi-stream heat exchangers. Okay, so I have tried to take the example problem from the paper, that the data is taken from this paper. Okay, so they have done single stage refrigerant cycle to liquefy the natural gas. Accordingly, there are multi-stage refrigerant cycle also present, where instead of just one refrigerant cycle, you have more than one, like 2-3 refrigerant cycles to cool down your desired stream. Okay, so first let's recall what is the refrigerant cycle. Okay, so this is a basic illustration of how refrigerant cycle looks like. So what we have here is we have hot vapor which is compressed at high pressure, and then it is cooled down in a condenser. So this condenser could be anything. So it could be water cooled, it could be air cooled kind of a thing. This high pressure vapor is condensed and is liquefied. It could be partial liquid also. Then this high pressure liquid is expanded via expansion valve, and in the expansion valve, due to the Joule-Thomson effect, the temperature of your steam further goes down, and it becomes further subcooled. That subcooled liquid, or either liquid or the mixture of liquid plus vapor, is used to cool down your desired stream. So let's say in case of air conditioner, we want to cool down warm air which is present in our room to a cool air. So this subcooled liquid plus vapor stream will be used to cool down the desired stream, and then from there, so it will become saturated vapor. That saturated vapor is again compressed and cool down. So this is one refrigeration cycle. I mean, you obviously might have learned it in 11th 12th curriculum as well as in your UG curriculum, right? So our typical air conditioning unit also operates on this way, where evaporator and condenser are both associated with the air cooling, right? So condenser is generally outside, where cold air comes and it takes the energy from this high pressure high temperature vapor, and we get the hot air outside. So that condenser is generally present outside the air conditioning unit, while the evaporator is inside. Okay, so this is a basic refrigeration cycle. Now how this cycle is useful in our case. So we have a natural gas. If we compare this, instead of cooling warm air to the cold air, we have a natural gas which comes into this multi-stream heat exchanger, which is at high temperature, and that is liquefied in this multi-stream heat exchanger. Along with this multi-stream heat exchanger, a refrigerant cycle is involved. So you can see you have a compressor where vapors are compressed, they are cooled. So here seawater cooler is used. This high pressure low temperature refrigerant goes into multi-stage heat exchanger, where it exchanges heat with the natural gas. Then again it's expanded via throttle valve. Again we get a low pressure refrigerant. Further that heat, like the low pressure low temperature refrigerant, which is at much lower temperature, will exchange heat from the natural gas, and it will liquefy the natural gas, and then high temperature vapor will go down to the compressor, where they are further compressed, and this cycle will continue. Okay, so why this multi-stream heat exchanger is used here? So if we will go into the Aspen Plus software in the simulation section, under the exchangers we have this M heat X problem. Okay, so what is the use of M heat X? So M heat X is used when we are mainly concerned about the heat exchange between multi streams. It could be that you have multiple hot streams, cold stream coming into your process plant, and then you don't want to specify, or you are not concerned about which two streams are exchanging heat as of now. You just want an overall heat transfer between this X number of hot stream and Y number of cold stream. In that cases we will use M heat exchanger. Okay, so if I show you here like this, here in this multi stream heat exchanger, what will be the composition, how this cooling will take place? So for that we will look at one process diagram, that what are the components of this multi-stream heat exchanger, and then we move forward. Okay, so we will do a problem and then I will try to explain how it is useful. Apart from that, multi-stream heat exchanger is also useful, as I was saying, that when we are not concerned related to the exact heat transfer between each individual streams, rather we just want to know overall heat transfer. So if you are familiar with the refrigeration of air, like air separation unit via refrigeration, so in that case is also there are companies which has this proprietary processes which help to separate the air into oxygen, nitrogen and the argon via this refrigeration cycle. So since this is a proprietary, then multi-stream heat exchanger, it's nothing but a white box where the component inside this white box are not specified, but only we get the inlet and outlet information, that where air inside comes and it's separated out, but what is happening inside, how much heat exchange is happening, how they are separated, that is not known. Same goes for this cases also, right? So what we will do, we will try to simulate this. For that, first, and let's add the feed component here. So what has been provided to us? So we have a natural gas which is being liquefied via LNG, and the refrigerant mixture. Refrigerant mixture is also given. So we will need the composition of this refrigerant mixture. So here molar composition of refrigerant mixture is given. It's made up of nitrogen, ethane, methane, ethane, propane and n-butane. So we will add all this component and then try to simulate what this LNG process. So first, let me add all the components. We have methane, ethane, propane and n-butane. For n-butane, let me search butane. Has anyone done that sound? Oh, I have to reload it. If anyone okay, now it should not leave the call. So if anyone joins, they can continue. So coming back to our example, we wanted to add n-butane. Just a minute. Okay, so n-butane is added. Now the property method that has been asked us is Peng-Robinson equation of state, right? So we will use that. And the property method, select Peng-Robinson. Just a minute. Then next, run the property analysis. Now let's go to simulation environment. So first we have this M heat exchanger. We have our natural gas which is coming on the hot side, since it's a hot stream which will be cooled down. it should be here. Reconnecting. So this is our natural gas Ng in, which is liquefied. So give them this convention. Now for our refrigerant cycle, what we have to do, so the refrigerant cycle inside flow diagram will be look like something that I will draw. I will include the reference from where I have taken this another reference from where I have taken the flow diagram of this M heat exchanger and refrigerant cycle. Okay, so we have first let's add the pressure changer, which is compressor. Let me rotate it.
Excuse me, sir.
Yes, just a minute. Yes, Nikhil.
सर डाउट है सर, जो वीक 9 असाइनमेंट में जो क्वेश्चन 3 गलत है वो सही है करेक्ट है नहीं?
वीक 9 असाइनमेंट में क्वेश्चन
पार्ट बी है सर, उसमें
मैंने चेक नहीं किया। सो क्या हो रहा है उसमें? आपके आंसर्स मैच नहीं हो रहे?
यस सर।
आई एम नॉट श्योर क्योंकि मैंने चेक नहीं किया है और किसी ने मुझे अप्रोच नहीं किया उसके रिगार्डिंग। सो इज इट लाइक
शेयर करें एक बार?
हाँ बोलिए।
स्क्रीन शेयर करें?
स्क्रीन शेयर करें आप? या गो अहेड।
ठीक है सर।
इफ़ यू आर श्योर कि आंसर में कुछ मिस्टेक है एंड आपकी मेथड करेक्ट है, देन यू कैन डायरेक्टली राइट मेल टू प्रोफेसर साहा। मैंने आगे भी अनाउंस किया है क्योंकि आई एम नॉट मेकिंग द असाइनमेंट्स, सो इफ आंसर्स आर रॉन्ग और देयर आर सम मिस्टेक्स और सम इंफॉर्मेशन इज मिसिंग, then I also have to inform Professor Saha. So rather than this becoming a two-way communication, you can directly mail him also. Okay?
हम पे मेल कर सकते हैं?
हाँ, आप लोग भी मेल कर सकते हैं।
मतलब कौन सी मेल आईडी में?
हाँ, प्रोफेसर साहा का मेल आईडी उन्होंने जस्ट अ मिनट, इट शुड बी ये वाला। सो नॉट दिस वन, उनका IIT गुवाहाटी वाला मेल आईडी। सो मैं ये चैट बॉक्स में आपके लिए रख रहा हूँ। ओके, सर ने भी शेयर किया हुआ है उनके लाइव इंटरेक्शन सेशन में। सो इफ़ यू आर श्योर कि असाइनमेंट में कुछ मिस्टेक है, आइदर बीइंग दी डेटा मिसिंग है या फिर आंसर्स आपके और उसके मैच नहीं हो रहे, देन यू कैन ट्राई इट आउट। हाँ बोलिए।
स्क्रीन शो रही सर?
यस यस यस
सर ये क्वेश्चन 5000 kg per hour for the equimolar steam flow.
हाँ, ethanol both at 1.5 bar heated to 19 degrees centigrade and available for heating. Use M heat blocks to solve and answer the following. ओके, तो इसमें आपके आंसर्स मैच नहीं हो रहे।
सर ड्यूटी ऑफ ऑपरेशन इज मेगावाट में तो ऑब्वियसली बातें को रिलीज होगा, अगर आप पढ़ो तो क्वेश्चन ढंग से।
ओके, नीचे जाएंगे, सारे आंसर्स मैच नहीं हो रहे।
नहीं सर, ये 3 बस।
ओके, सो लेट मी चेक।
ड्यूटी ऑफ ऑपरेशन अनलाइक तो वो रिलीज ही करेगा ही, आई थिंक, जब वो मतलब इतना हाई।
ओके, लेट मी चेक, मैंने देखा नहीं है, सो आई विल ट्राई इट आउट एंड विल लेट यू नो। ओके, आप एक बार
क्यूएनए में सब बच्चे का करेक्ट यही था, मतलब बहुत बच्चों ने यही आंसर दिए।
Okay, so I will try this problem out, and if there are any mistakes, I will also mail Professor Saha. Meanwhile, you can also directly mail him that there is an issue in the answers. Okay. right? So if you want, just remind me regarding this issue via email. Okay, so I will try to do it in 1 or 2 days. So yeah, anything else? So I will continue
What's
if
that?
nothing. Okay, so I will continue with the today's class. So now we have to create the refrigeration cycle. Okay, so from compressors, the high pressure vapor will be further cooled down via any heat exchanger. So यहाँ पे sea water heat exchangers दिए हैं. Okay, just to rotate it. Compressor outlet is further cooled down, and that will go here. We need a pressure changer, so let me add a valve. First I'm creating this flow diagram, and then I will explain it to you what is happening and how is happening. Hot product outlet, this should be rotated further.
आज तो मॉडल भी नहीं देखा, कौन सा मॉडल यूज करेंगे? Which model यूज?
For what?
सर जो अभी क्वेश्चन दिखा है इसमें मॉडल कौन सा यूज करेंगे? ना उसमें मॉडल देख ना कुछ, मतलब मॉडल पैरामीटर नहीं देख, मेथड्स नहीं देख.
Property estimation method.
Yes.
Okay. So if nothing is given, you can try it out. This NRTL or unified method. It's ethanol and water mixture, right? So that should work, and it's a heat exchanger example, right? So it should not make much difference. Property method. It could be that the method, although method should not make that much of a difference. But if ideal method is used in the calculation and you might have used another method, then there might be slight difference. Else other method should not give a drastic difference. So let me see. I will try it out and will let you know. Okay. Now from this, and cold product will go to our cold. Just I'm reordering it, then I will explain what is happening. Reconnect. Okay. So this is how your cycles should look like. So this is our refrigerant cycle. So what is happening, that one is our natural gas is being cooled down, so that is hot stream being cooled down to and that we want to liquefy, so we are getting an LNG. And then we have our refrigeration cycle, so where our hot vapor are coming, which are compressed, then subcooled. This subcooled high pressure stream is again going into M heat exchanger. This is going on the hot side. Okay, from there its temperature is further reduced, So this high pressure low temperature stream then goes to the valves where it is expanded, and because of the expansion and Joule-Thomson effect, the temperature of your stream will go further down. So that subcooled stream that will be used as a cold stream in our multi-stream heat exchanger, which will exchange heat from both natural gas stream as well as our high pressure cooled stream. So that will exchange and cool down both of the stream, right? And then from there evaporated low pressure stream will go to compressor again, and this cycle will continue. Okay, so this is how our single stage refrigerant cycle to cool down to liquefy natural gas will work out. Okay, so this is our information that we have. Now let's try to simulate it. What is happening here? In our problem statement, what other information we have? So we have a flow rate of the natural gas, flow rate of the refrigerant is given, pressure value is given, that natural gas is coming at 5.5 bar. These values are in the bar. Okay, so it's a megapascal. So you can convert it as like 55 bar, right? Refrigerant pressure is given. So HPR, which is high pressure refrigerant, LPR is low pressure refrigerant. So high pressure, where high pressure will be created, that will be at the outlet of your compressor, right? And low pressure is 0.24, so which will be at the outlet of your valve. Okay, so since valve is used to depressurize the stream, so that is 2.4 bar. Temperature value is given. So inlet temperature of natural gas is given. Inlet temperature, like for the refrigerant, is given. That is high pressure refrigerant is at 305 Kelvin. Okay, there are some unknowns here. So in between temperature for this refrigerant cycle is not known to us. Outlet temperature of natural gas is provided and its molar composition is provided. So this U4, U1 and U2 are unknowns that we have to figure out on our own, that what should be this temperature. What other information do we have here? So same information has been stated here. So let's try to simulate it and then see what should be the other possibilities of this unknown temperature that we should put. First, let's edit the natural gas. So natural gas is coming at 1 kilomole per second flow rate, 25 degrees centigrade and 55 bar. So 25 degrees centigrade, 55 bar, and flow rate is 1 kilomole per second. Okay. Composition of the natural gas. So composition is provided here, that we have 1% nitrogen, so 0.01, methane is 95.6, so 0.956, sorry, ethane is 3.1, propane is 0.2, so 0.031, 0.2 is 0.002, okay, and rest 0.1% and butane, and these are the mole fractions. Okay, so these are the total mole flow rate is 1 kilomole per second and mole fractions has been provided. Go to next. Now it is asking for the information about the heat exchanger. Okay, so NG is connected to LNG and outlet temperature is provided as 110.15 Kelvin, or as you can write it as minus 163 degrees centigrade. So I am providing the outlet temperature for LNG as minus 163 degrees centigrade. Okay, so this information we have. Now for S4 and S6, S4 is our cooled high pressure stream, which is further cooled down to S5. Okay, so in M heat exchanger, S4 will be connected to S5, and S6, which is low pressure low temperature stream, is connected to low pressure high temperature S7. Okay, so this S6 will go to S7. Now we don't know what are the temperature values here, that we have to think about it. Okay, so we have to think about what value to put. Either we can put any one value, we have to write either this hot stream value or the cold stream temperature value. That right now we don't know, so we will keep it as it is. What other information do we have? So let's see. We have the compressor information. That compressor outlet is given as high pressure refrigerant is at 36.95 bar. So if I go here, let's mention the discharge pressure. No specific information on the compressor is given, so we will select isentropic compressor, and the discharge pressure is 36.95 bar. Okay, so compressor information is complete. Now we have the molar composition for our feed. We have its flow rate. Okay, refrigerant flow rate. So we can provide this information to either of this S3, S4, S7, S6 or S5, since all this loop is for the refrigerant. So what condition should we select? If you will think about it, at the inlet information of S4, we have the one inlet temperature of high pressure refrigerant at 305 Kelvin, which is our inlet information. Okay, so it is S4 will be our best guess, since in the S4 what other information we will need apart from flow rate and composition? We will need the temperature and pressure value, right? So pressure value can be said, since it's a high pressure refrigerant, same pressure will come here, right? And temperature value is also provided. If you will see, inlet temperature is 305 Kelvin. In here also, the refrigerant is compressed at 36.65 bar and then cooled using seawater cooler that passes through a heat exchanger where it condenses, expands across a Joule-Thomson cycle. Okay. So that is the best guess that we can provide here. So let's try it out. First we will provide the heat exchanger duty where high pressure refrigerant, this is cooled down to 305 Kelvin. Let's provide zero pressure drop across the heat exchanger. Okay, so this information is complete. Compressor information is complete. S4 information we will put, which is a feed stream. So this is coming at 305 Kelvin. Pressure value, so it's 36.5 bar, right? Molar flow rate. So molar flow rate of refrigerant is given as 3.47 kilomole per hour. So let's select that 3.47 kilomole per second, sorry. Kilomole per second. And these are the composition. So nitrogen is 15.32, methane is 17.79. So nitrogen 0.1532, methane 17.79. Ethane is 40.85%, 85. Propane is 0.41% and butane is 25.62%. So 0.2562 and propane was 0.41%, right? So 0.0041. We are missing some information. 15.32, 17.79, 14.85, 0.0041, 25.62. And these are the mole fraction. Okay, 3.47. Let's take it as 0.42 just to round it off, overall mole fraction to 1. Okay, so this is done. So now our refrigeration loop its composition is fixed, its flow rate is fixed. So we need to specify any one feed composition here, right? So that we have done. What other information we have? We have information across this valve. So what is the pressure reduction? What is the outlet pressure of valve? So low pressure refrigerant is given as at 0.24 megapascal, which is nothing but 2.4 bar. So outlet pressure for our val is at 2.4 bar, right? Now, if you will look in the overall diagram, what what other things we are missing here? So we have compressor outlet. So this stream we are okay. We have heat exchanger details. We have provided outlet temperature. So this is okay. S4 temperature pressure condition composition is provided. Now S4 to S5, what should be the temperature reduction, that we don't know. So temperature of S5 is unknown. Pressure drop, let's say we will assume is 0, then pressure drop is also fine. So pressure value is known, composition will be same, that is known. Val information we have, and based on that we will get some temperature of S6. So inlet temperature of cold stream we don't have to worry about. Okay, then from there what should be the outlet temperature of the cold stream? So that will be calculated based on the heat duty of the hot side, and we will get the outlet temperature of this cold stream. Okay, which will go to the compressor, the outlet temperature of the cold stream which is being evaporated, and that will go to the compressor, and the cycle will continue. So we will need temperature information at either S5, or we have to provide information at S7. Okay, so we have to make some guess here. So what is happening in this cycle? Let's try to understand it. This hot vapor are coming, they are cooled, they are further cooled to some degree, then they are expanded. So because of expansion, this high pressure stream, high pressure low temperature stream is further converted to low pressure low temperature. That low pressure low temperature is used to heat up, to cool down our natural gas as well as this intermediate stream. Okay, from there low pressure high temperature stream goes to the compressor, right? So one thing is, the S stream is going to the compressor. The condition of S7 should be such that the all the component of the S7 are in the vapor phase. Like molar vapor fraction of S7 should be 1. Okay, that should be the one condition that we can understand. For the valve, near the control valve, what we have seen here, that from the condenser this will come to as a liquid phase. Okay, so the S5 is generally liquid, which is expanded, and then it gets converted to vapor plus liquid or completely vapor phase, depending upon the how much throttling we are doing. So this information also we have. So what we can do, either try to provide a temperature of H5 such that this stream here is somewhere around liquid phase, or provide the information of S7 such that this S7 is at the vapor fraction. So I will try to start with the S5. We will provide the outlet temperature of S5. For that, let me try and select. I am providing one information as minus 160 degrees centigrade. This value is selected based on the dew point. So this is a guess, but this guess is a calculated guess based on the temperature, like dew point temperature for this refrigerant stream. Okay, and then let's see what is happening. So if we, with this information, if we try to run the simulation, it's processing. Results are available, and we haven't got any warning. So this shows that our guess worked, but let's try to analyze the feed condition here. Okay, so our M heat exchanger block is B1. Go to the stream result of B1. In the B1, what we saw, first Ng is connected to LNG. Let me just rearrange them. Then
sir, which refrigerant is used in? Sir, कौन सा refrigerant use हो रहा है यहाँ पे?
It's a mixture. So mixture of nitrogen, methane, ethane. So it has been provided. See, the composition of refrigerant is provided. Nitrogen, methane, ethane, propane, and butane. So that is the refrigerant.
Methane and ethane to natural gas है. So include this.
No, so natural gas stream is this. Okay, जहाँ पे main component 95% you have methane, which is our main focus, and we want to liquefy it. For the refrigerant,
which compounds are enrolled for the refrigerant? nitrogen, ethane या propane?
No, it's a so refrigerant are generally mixture of this low molecular weight your hydrocarbon. So it could be combination of ethane, propane,
So
propane,
outlet
butane.
of methane is less.
Outlet.
Methane तो कम हो जाएगा ना सर.
No, this is
Overall
not an
methane तो कम
outlet.
हो.
See, this is not outlet. See, again, understand here. This first stream, the natural gas, this is coming at flow rate of 1, pressure of 55 bar and 25 degree centigrade, and then cool down to 110. So composition is not changing. This stream is just heat exchanging and then going out. For this refrigerant cycle, which will exchange heat from your natural gas, you will need some refrigerant, right? So that refrigerant which will flow in this loop, that is a mixture of nitrogen, methane, ethane, propane and butane. Okay. Now why this specific composition? That could be because this composition might give you a better refrigeration efficiency. Okay, so generally this refrigerant, if you will search, they are composition of lower molecule weight hydrocarbons. So it could be ethane, propane also, propane, butane also. Okay, so right now the information that I have selected from this publication, this one Watson et al., they have selected this refrigerant. Okay, but these are two different streams. It's not that they are not mixing together, only heat exchange is happening. So for refrigerant loop, only heat exchange will happen with the natural gas, so that's a separate part. Okay, you got my point?
सर ये नेचुरल गैस ही खुद का रेफ्रिजरेंट बन रहा है, मतलब यूज कर रहा है.
खुद का as in no, not खुद का, वो it's not exchanging heat within itself, it's using another refrigerant. So but yeah,
ना another refrigerant is not used. It's मतलब कुछ another refrigerant use नहीं कर सकते.
let's just see what are the common refrigerant.
अरे बैड रिजल्ट तो नहीं देगा ना, मतलब ऐसे रिजल्ट रेफ्रिजरेंट यूज नहीं करें.
No. So what are the general? So initially, see, chlorofluorocarbon is not used now. It was initially used, but it's banned. So these are the various refrigerant used. Hydrofluorocarbons. So natural
अमोनिया
refrigerants.
सर यूज कर सकते हैं. अमोनिया इज द बेस्ट रेफ्रिजरेंट.
Yeah, so this is just an example. So see, here they have used hydrocarbon as a refrigerant. So natural refrigerant like propane and isobutane belong to this category. So the some combination of propane and isobutane can also be alone used as a refrigerant. Here only, instead of only just using propane and isobutane, the reference that we have selected, they have used nitrogen, methane, ethane, propane composition, propane to n-butane composition. So that's it. As in there are other refrigerant also, as you are saying that ammonia is also a good refrigerant that can also be used. Okay, yeah. So coming back to our results, so let's see the stream results. Yeah, S4 is connected to S5 and S6 is connected to S7. Yeah. S4 is connected to S5 and S6 is S7. So what is happening, that first let's look at the natural gas Ng, which came at 25 degree centigrade, cooled down to minus 160 degree centigrade. Okay, and we got an LNG. Intermediate stream, so intermediate subcooled high pressure stream, so that is S4, which is coming at high pressure of 36.95 bar and temperature of 31.86, got further cooled down to minus 160 degree centigrade and 36.95 bar. From there, what happened? This minus 160 degree centigrade and 96.95 bar stream went to the our B4, which is our valve, throttling valve. Okay, and there it expanded due to Joule-Thomson cycle, and from minus 160 temperature went to minus 165.6 and pressure went to 2.5 or 2.4 bar. This we had provided. So due to this expansion, stream pressure went down. Okay, so instead of liquid, now our stream became some combination. So molar vapor fraction is 0.133. So it became a combination of vapor plus liquid stream. It's a mixed stream. Okay, that mixed stream, that S6 is again coming as a cold stream into our M heat exchanger, where it will exchange heat from both S4 and natural gas, and then this low pressure high temperature stream will be generated, which will fed into the compressor. So
सर जो LNG है उसका टेम्परेचर बहुत
yes
माइनस में नहीं जा बहुत ज्यादा है
yeah it's
-160
हाँ so what is the
आइडियली पॉसिबल है सर ये
yes it's possible. So these are the commercial methods. So overseas mein, all the overseas transport of natural gas, that is done by this liquefaction process, where near the seaport you have this liquefaction units, LNG units, where natural gas is liquefied, then it is transported, and then again it's expanded and converted into the gaseous phase. So it's a commercially
so -163 में वो liquefied रहे I think.
Yes, so if you will see, let's go to the property analysis.
Using for optimization use कर सर.
Let me show you the feed specification. If you will see, what is the normal boiling point of natural gas? It's taking that time. Let's search here only. Right? Boiling point of methane at 1 atmosphere. So it's a 65 degree centigrade and boiling. Not methane, methane. So it's like, see, -161 point. So we have, if we are at atmospheric condition, we have to lower our temperature till this spot. But right now we are at 55 bar. So 161 works well, and then methane will stay as in a liquid state, right? So this will work out.
This is sure.
Now it has stopped responding. Just let's wait for it to respond. So what other information do we have here? We have to find the overall heat transfer coefficient, compressor load, generate temperature, enthalpy composition curve for both cold and hot stream. Okay, these are the small things. But mainly I want to analyze this result, what is happening. So let's wait. So here also you can see the boiling point for your methane is -161 that we already saw, right? And this other component also are has a much lower boiling point, while for propane and butane, and the boiling point range is fairly closer to the absolute zero degree centigrade. Okay, that's why they are the better choice compared to the nitrogen and ethane alone, while the mixture can also be used. Okay, so coming to the simulation again. So as I was discussing that, oh, this data went away, I have to rerun it. should complete by now. Let me close this. Don't need this information. So Nikhil, I have also included that decanter example that you were discussing last time. So
Sure.
three decanter in a series. So I think that's the third example for today's session. So once we are done with the series of heat exchanger example for hydrocarbon separation, that third problem I am also discussing. Okay. Uh, I think we will have enough time to cover question 3. Question 4, I don't know whether we will be able to cover it today. Anyway, let's see. Yeah, so results are available. So what we were discussing, yeah, the outlet of B4. I wanted to interested in that. So that 160 degree centigrade steam is expanding to 165.6. This will be used to cool down both natural gas and intermediate stream. From there, the S6, which is cooled steam, it will exchange heat from both natural gas and intermediate S4, and then see, you can see it has exchanged it and its temperature came to minus 7.96 degrees centigrade, and it completely became to a vapor phase. So what this M heat exchange is with respect to refrigerant cycle. So it acts as it will act as an evaporator, right? So in our refrigerant cycle, what is happening, that this high pressure low temperature refrigerant is throttled and then further cooled down, and then low pressure low temperature refrigerant, yeah, this will be better. Low pressure low temperature refrigerant is fed into the evaporator where outlet stream is cooled. This liquid plus vapor stream, mixed stream, is completely evaporated to a vapor phase, fed to the compressor, and this cycle will continue. So that thing is happening, right? So this low pressure high temperature stream is such that the S7 is completely in the vapor phase. So what we did here, we had provided information of S5. Instead, so S5 we provided as minus 160. Let's say I know that S7 should be at should be in a vapor fraction, right? So I provide that, and I delete the information of S5 stream, and then see what is happening. So there are some errors. Let's see what it is. The following unit operation block were completed. B1. Cold side stream S6 is losing heat. S6 is losing heat. S6, yeah, it should lose heat. Just a minute. S5, and then this is our S6, which is coming at 398. S6 is coming, and S6 and S7. So minus, okay. So for the vapor fraction, it has changed the temperature value to 398.344. Okay. So the optimization that this stream has done is not well. It's not working well for us. So instead, we will stick to that temperature part. Minus 160, and let's omit this. So this is not working well for us. Reset this simulation and run it again. another thing I wanted to show here was that basically this process is much sophisticated, that some few degree change in this S5 or S6 will give you an multitudes of error. As in, let's say your stream temperature you have selected as such that this input to a compressor is not completely a vapor fraction. Okay, it has some amount of liquid present in it. Then it will give error in your compressor part also. Similarly, if your temperature, intermediate temperature S5, you have selected too low or too high, then crossover inside the M heat exchanger, temperature crossover of hot and cold stream inside the M heat exchanger can also happen. So that sort of an error you will face. So right now I had done this some trials in the range of S5, and then we landed with the value of minus 160 degrees centigrade. That worked, but it might not work, so you might have to do either some sensitivity analysis or some trial and error thing to identify the mistakes and complete this loop. Okay, so let it finish, and then we will just see the enthalpy versus temperature curve, and then move ahead with the second problem, since anyway we are running with away from the time. So now it's working. Stream results S6, S5 and S6. So yeah, minus 165 going to the minus 7. So this works for us. Okay, so we'll stick with this result. What has been asked us is what is the load of what is the exchanger duty here, right? Overall heat transfer coefficient, compressor load, and temperature versus enthalpy curve. So you have Kw, we have the duty. From duty, can we compute the heat transfer coefficient? Yes? Yes or no? I think we have done it previously, right? So we can use this duty amount to calculate the heat transfer coefficient. So that can be done. In the compressor load, so compressor is B2 compressor load. So this is the horsepower, you can see 33416.9. For the enthalpy versus temperature curve, we can go to the M heat exchange part. In the result itself, you will have that is not the parameters. Sorry, this is the compressor output. Yeah, here. In the result section, you have a balance, exchanger, and zone profile. What happened? Result. That should be zone profile generated here. It's not done. Let me check again. Dynamic input zone analysis. Let's say we provide 10 points for zone analysis, then we should have this. Yeah, so we have a zone profile, and then accordingly how temperature values are changing. So if you will see Q versus, let's say, T hot and T cold, temperature of hot and cold stream, so you can visualize it, that how they are changing. And you can see at the lower end, this both hot and cold stream are fairly close to each other. So our gas of 160 if it might have been somewhere off, let's say to 165 or something, then temperature crossover in this zone would have occurred. Then in that case you might have got this error of temperature crossover. So if you will try when you will try this example on your own, try to see what temperature values you can put it in without getting any error. So we have selected outlet temperature of S5 as minus 160. Try minus 155, minus 162 and see whether you are crossing this zone profile or not. Once you will see that, you will be able to compare it. So even in the given example, the reference paper that I have taken from, you can see our zone profile and that zone profile is almost matching, right? So these are the kind of a same trend that we have with the close proximity of hot and cold stream at the lower temperature end, where we have to be much careful. Okay, so this is an example of M heat exchanger. Let me save this file first, and then we can move ahead with the next example. Okay, so for a next example, let's start the new simulation and dive into the second example. So what question number 2 states to us? So we have been given a hydrocarbon stream H, which is at 5 degrees centigrade and 2.5 atmosphere. Okay, the pump has discharged the liquid feed F at 5 atmosphere. So this hydrocarbon stream is coming into the pump. It is discharged at 5 atmosphere, and component wise flow rates for this stream H are provided. Okay, in the figure below, the schematic representation of hydrocarbon separation process integrated with pumps, 3 DSTWU columns, 2 red flag columns is been shown. So this is our process flow diagram, how it looks like. So we have a hydrocarbon stream which is pumped, then is fed to the DSTWU unit. Vapor product of that unit are separated via red flag column, while the liquid product is separated via DSTWU unit. And similarly, same case, the liquid bottom product of the red flag column is separated via DSTWU unit. Okay, then further information on this is given, that all DSTWU fractionator have 20 stage each, including condenser and reboiler, 2 RECT model. So RECT, this is nothing but a modification of red flag column. So here what has been said to us, that we have 2 red flag column, CR1 and CR2, but if you will see here, both of them does not have any reboiler in it. Okay, so that's a modification of red flag column, which is referred as RECT. Okay, they have 10 stage each, including container reboiler with no reboiler. The specification of all these 5 distillation unit is shown here. Then we have to use the Peng-Robinson property method to simulate the separation process, compute the flow rate and composition of all these streams. Okay, so this is a very basic example. Do any of you want to try it out on your PC? Is it possible? Nikhil, I know you are using phone. Rohit, would you like to try it out? If you can share your screen and solve it, or should I do it? Okay, okay then, anyway, I will do it, no worries. Just a minute. So we have C2 to C6 mixture. Okay. Oh, here I forgot to provide the details. So this should be let me just check. This should be isobutane, N-butane, isopentane, and N-pentane. Just let me quickly confirm this. ISO N, and then we have NC6 also. So this information is correct. We have N-hexane. Let's add this component to our list. So first let me add ethane. Then we have propane. For butane we have to add both N-butane and isobutane. So we will search for that. Butane. Oh, shit. It came and I closed it. We have 2, 3 or 9. Okay. All the light key information is there and pressure values are there. So first add isobutane, then we have N-butane, then for pentane also we have to search for both isopentane and N-pentane. Added and that is not working. Let's try. If it will take too much time, then I will open the already pre-run simulation and then we can go with that. Pentane, I'm writing it correctly. Okay. Recording is well. Okay. Yeah. So we want to add isopentane, then N-pentane, add. Okay, and last we have hexane. So N-hexane, add that. So all the components are added. Let's go to the property selection. If you want, you can change the name. Let's put it C2, rename, C3, rename, IC4, rename it, NC4, IC5, NC5, and then we have NC6. Okay. Property method has been asked us to use Peng Robinson. run the analysis. Now here also, what do you think, what should be the separation pattern? Okay, so obviously with the increase in number of carbon values, boiling point will increase, right? But then which component should come from where? Can you guess it out? So this C1 here, we have been provided that light key for C1, which is DSTW1 unit, is butane, while the heavy key is pentane. So bottom product should contain mainly pentane and hexane, that will be separated from C3, while from C1 to C4 should go into the top part. That top product will go into the red flag column. From red flag column again, so now here we have C1, C2, C3, C4. So C1 should come out from DR2, C2 should ideally come out from DR2, and C3 and C4 from here. Okay, that's what we expect. Let's see whether this separation is happening or not. If you want to check out the normal boiling points, you can use this review part where you will find the properties, various properties of all the components that you have selected. So as we had seen that a boiling point, so boiling from point from going from C2 to C6 should increase, right? So while for component NC4, yeah, same is happening. Like this is the lightest component, like light key component in all the mixture. Then the boiling point is increasing with the change in the number of hydrocarbons, like number of carbons present in the hydrocarbon. Okay, now let's go to the simulation part and simulate our process. Okay, so this is the flow sheet that has been provided to us. So we have first pressure changer, pump. From pump, our stream will go to C1 unit, which is DSTW unit. Bottom product of that will go to again another distillation unit. Top product will go to the sorry, this should be top product goes to the red flag unit, and the bottom half of the red flag is again coming to the DSTW unit. Now for the red flag column, if you will see, you have multiple options. We have to select this RECT, which is red flag without any V boiler unit. Okay, so we have two such red flags column. Okay, so this is how your process flow sheet should look like. Now let's connect all the streams. So we have feed H, like that, going to the first distillation column. Bottom product of that, sorry, top rod, this is the bottom. From here we will get one distillate. I'm not able to connect bottom product. This goes to the third column. From here again we have distillate and bottom. The top vapor goes to here. Okay, so this is how your process flow diagram should look like. Let me slightly modify it for better representation. Reconnect source, it's coming from here. And let's rename it according to the problem statement. So this is H, which is coming into our pump. Let's put it as P. This is our feed. Okay, then first column is referred as C1, this column is referred as C2, this is C3. Okay, then we have for this notation are CR1, CR2, and corresponding D1 D1, D3 D3, D2 D2. Okay, so let's say, so this is distillate 1, bottom 1. This is actually C3, so let me C2. Corresponding top product is D2, bottom product is B2, C3. These are D3 and D3. Okay. Now this one is referred as CR1, top product as DR1. This is DR1. CR2. DR2 and so all the connections are provided. Now let's put the input data. Block C1 required output. Oh. Now let's put the input data. So first we have stream H, which is coming at 5 degree centigrade, 2.5 atmosphere, and these are the molar flow rates. 5 degree centigrade, 2.5 atmosphere, and molar flow rates are given, right? So let's put it in 35, 50, 130, 35, 50, 130, 200, 180, 205, 180, 205. So these are the flow rates in kilomole per hours. From that, pump outlet, that is discharge is at 5 atmosphere. So I will first provide the pump outlet. Discharge pressure is at 5 atmosphere, right? Now we will go to the C1 unit, input of C1. C1, the data for the distillation units are given here. Okay, so all DSTW unit has 20 stage including condenser and reboiler. So total number of stages are 20. Light key component for this is NC4, right, with 0.99% recovery, 0.99 mole fraction recovery, and heavy key component is IC5 with a recovery of 1%. So select it as 0.01. Now for the condenser part, it has been provided that the operating pressure for first column is 4 for both condenser and reboiler, 4 atmosphere, and condenser is partial condenser with all vapor distillate. So 4 atmosphere, reboiler is also 4 atmosphere, and condenser here is partial condenser with all vapor distillate. So what will happen here, that your top product, although the represent shows it's kind of a distilled, like it's condensed and it's in liquid phase, but it is in completely in vapor phase, and that is fed to your CR1. Okay, now at what location in the CR1 it will be fed, that will also we will discuss, and why that particular location, that is also a thing to understand. For C2, specifications are given, so let's go for C2. Again, total stages are 20. Pressure values are 1.5, 1.5 with total condenser. So 1.5 atmosphere. Reboiler is also at 1.5 atmosphere. Light key here is IC4 and heavy key is NC4. So light key IC4, 99% of that, heavy key is NC4 and 0.02%, 2%. Okay. Then for C3 we have further information. So go here, C3 again 20 stage, light key is IC5 with 0.99% recovery, heavy key is NC5 with 0.01 mole fraction recovery. Sorry, it's 4%, so 0.4. Again here also it has total condenser and pressure value of 3 atmosphere. Okay, go next. Now we have to provide information for red flag column, which is CR1. Red flag column has both 10 stage. Now the condenser type. So for first CR1, condenser type is partial vapor. So we can see partial vapor, select that. Now as we said that there are no reboilers, so reboiler select as none. Since we have selected reboiler as none, we will need fewer information in this matrix. So what information we have? We have distillate to feed ratio as a mole basis, which is 0.2. So distillate to feed ratio, if we will provide it as 0.2, the second information will go away. Since we don't have any reboiler, we don't have to provide this information. Last time we had looked at similar example where there was no condenser. So in that case also we selected condenser as none and we only had to provide one information, right? Now let's provide the stream information. Stream stage. So here there are no stream stage provided. Okay, at what location CR1 or CR2 feed is coming in both of these red flag column, which is needed, right? We have total of 10 stages. If you will see, in both of them it is shown that feed is coming at the bottom. So we have total 10 stage. So let's say feed is entering at some stage number 10, but still it's not going, this red mark is not going. Let's press next. So it shows completion error, that feed or pump around to the bottom stage must be specified when reboiler is equal to none or reboiler duty is 0. Essentially when you don't have a reboiler. So in the form of on stage feed to the number of stage or an above stage vapor or liquid feed to number of stages plus 1. So if we are providing feed on stage, so that should be at the number of stage. Let's say we have n number of stages, so it should be on stage number n, or it should be above stage number n plus 1, right? So what does it mean? It wants to say that, see, here we don't have any reboiler, but reboiler is needed in the distillation column to provide a heat duty, right? Where your bottom product is converted to a vapor, like that. So reboiler will provide heat duty to your distillation column. But here if we are not providing it, then how vapors will be generated? So for that, the vapor outlet of your for the previous distillation column is directly feed into the bottom. Okay, so heat for the distillation column will come from this vapor outlet, okay, which is fed at the bottom. So feed should be at on stage 10, it should be at the bottom stage, and once we do that, you can see it has turned into green. Now the pressure value. So for the red flag column, pressure value is given as 2 atmosphere. Let's provide that. And last we have CR2 information to feed. Again CR2 10 stage. Condenser type here is total condenser. Distillate to feed ratio is 0.5. Pressure is 1.5. Okay. Condenser type total condenser. We don't have any reboiler, so we will write it as none. Distillate to feed ratio is 0.5, right? That's 0.5, and pressure is 1.5 atmosphere. So pressure 1.5 atmosphere. Now again stream, so again here also yes. Yeah, I mean, so again here also feed should come at the bottom. Okay, so here also if you will see, we had selected condenser as a partial vapor, so the top product of CR1, red flag 1, will be in the vapor phase. That should go at the bottom. So that will provide heat to our distillation column, right? So feed stage should be stage number 10 on stage number 10. I hope you are understanding this concept, right? So since we don't have a reboiler, heat duty for the distillation column will be provided via the vapor outlet. Okay. If you want, you can rearrange them here by putting him down. Okay, it's just a way of representation, nothing else. Everything else remains same. Okay, right? So this looks more like to what the problem statement has. So we have provided all the information. Now just we have to run the simulation and see how separation has worked out.
सर जो नो यहाँ पे जो ईओ कंट्रोल लिखा है उसका मतलब क्या होता है?
Which control?
ईओ कंट्रोल एस्पेन क्लास में लिखा है ना, कंट्रोल पैनल के नीचे.
Oh, this thing.
Yes.
यहाँ पे हाँ, एक मिनट.
What means that, sir?
I'm not aware about it. Let's see. एक बार इसको पहले रन हो जाने दो. So is anything else has been asked here? No. We have to just simulate the separation process to compute the flow rate and composition of all product rates. That's it. Nothing specific has been asked. Okay. Let it load. Meanwhile, we can start discussing the idea of the third question. Once this is completed, we can discuss the result. So third question, I think last time you had asked Nikhil. So this is the same example. So we have a mixture of ethyl acetate and acetone with 78% ethyl acetate. Ethyl acetate has to be extracted from 1 kg per minute. So that of this mixture. So feed flow rate is given as 1 kg per minute in a 3-stage extraction process using decanter with 1 kg per minute of water at each stage. So what is happening, you have 3 decanters in a series. Okay, so this is something like this. So you have decanter 1, decanter 2, decanter 3. Your feed is coming. You have your solvent, which is water in this case. Both also has a flow rate of 1 kg per minute. That is also coming in this series. Now in the decanter, the extraction process will take place, and you will have some separation. Two phases will separate out because of the liquid-liquid phase equilibrium. Raffinate will go to the next column. You will have one E1 extract here. That raffinate will again solvent will be added to that, and you will get extract 2 from the second decanter, raffinate of second decanter will again go to the third decanter, where again water is added, and you get the third extract and last raffinate. So this is how complete process has been shown to you. Okay, now all the decanters and the feed of the first decanter at 25 degrees centigrade and 1 atmosphere. So operating condition is given. We have to use NRTL property estimation method along with the unifact data to estimate the binary parameters, and some of the question has been asked. Okay, so it's a straightforward. So instead of using an extraction column with, let's say, 3 number of stages and continuous feed of water, stage wise extraction process has been used with the help of decanter. Okay, so we will see this also now. Yeah, this has completed. Okay, so first let's look at the results, stream results. So what will happen if here, yeah, you wanted to see this EO modeling part. Okay, I'm also not fully aware about it, but we can check it out. No data to display. Equation oriented model to, okay, so it's an equation oriented model. So rather than using Aspen plus equation data, if you want to use your own data, okay, configure value of attribute for variables, specification group. Sorry, can you repeat it?
Can you just look at the assignment number 10 question? I think some parameters are missing there.
Assignment number 10, this week assignment.
Yes. Yes. And the previous year, me and Matt this is all that assignment, but our all answers are wrong. I think.
See, I have even Nikhil was saying that. So if you are sure that you haven't made any mistake, then you can directly write to Professor Saha. What I will do, I will check that assignment and try to solve it, and if I find it same error, I will mail it to him. But again, I'm not making any assignments here. That is done by some other TA at IIT Guwahati, and they evaluate it. Okay, so it's outside of my area, as in, so even if you will say it to me, I will again mail it to Professor Saha. So rather than becoming a two-way communication, you can directly mail him, and then he will sort it out. Okay, once you are 100% sure, okay, that you have done what you have done is correct, I will also check it out and will let you know. Now you are saying this week assignment. Okay.
Yes, sir.
Yeah.
Can you just look at this one?
Yeah, I'm looking. Assignment week 10, assignment 10. Because I had asked one student, he said that he has submitted it, so I'm not sure. Okay, so we have 4.5 kg of an equimolar binary mixture of N-heptane and toluene separated by extractive distillation at atmospheric pressure. Okay, using NMP as a selective solvent. Okay, extractive distillation, a column with a separation ability of 12 stage using total condenser and kettle reboiler are used. The feed mixture is at bubble point with a pressure of 110 kilopascal, enters at the 8th stage. The selective solvent removes toluene and they are obtained in the bottom product. Okay, the N-heptane has to be recovered in the distillate. The distillate flow rate is equal to the molar flow rate of N-heptane in the feed. The reflux ratio is 3. Toluene separated from NMP in a second atmospheric distillation column with 8 stage, and a second atmospheric with 8 stage including total condenser in the boiler, where the reflux ratio is 2.5 and distillate rate equals to the mole flow rate of toluene in the feed. The feed enters the 4th stage of the column. Using Aspen plus simulator of this system, if NMP mole flow rate is, if NMP flow rate is 630, 100 degrees centigrade and pressure is 170. If it enters at 3rd stage, use NRTL property method, binary data. So you have first distilled red flag column where you have both the solvent data, right? Like feed stage is also given, solvent stage is also given, feed composition, solvent composition is given.
What is its feed temperature?
Sorry?
They mention at bubble point, the feed temperature is after that.
Sorry, can you repeat? They have mentioned at bubble point. So you can use Aspen plus, right? As in you have various properties. So here you see. Uh, Let me put another red flag column. Okay. Now in this red flag column, uh, instead of having it, you have one stream coming. We connect to destination. Okay. Okay, so this is your stream. Now you have this other option, right? So let's say pressure and vapor fraction. So you write what is your pressure value here. Pressure value for feed is given. That
Yes, 1 1.
Okay, so it's 1.1 bar. You provide it as 1.1 bar, and vapor fraction. So you have to write vapor fraction, right? So feed, what is it? Feed is at bubble point.
Bubble point. Q is equal to 1.
Okay, so your vapor fraction will be 1. That's it. So your feed data is complete. Flow rate is given. Okay. So this data is complete, and what I can understand from the statement, red flag data are also given. So for red flag, what else you will need is I think that's a red flag, right? The reactive distillation column, NMP 12 stage kettle reboiler location. Hi. So since we have to use a location, so you have number of stages given, condenser reboiler type given, distillate to feed ratio is given, right? Okay. Distillate flow rate is given. 8 stage they are obtained above the bottom. Reflux ratio is provided. So I guess all the data is there. Stream location you will
Can
know.
you just click on pressure parameters?
Pressure parameters
What
for
we have to bring?
pressure parameter for column.
They mention stage 1, stage 2, but we don't understand what to fill there.
Just a minute, stage 1. An aptane has to be recovered. Flow rate is equal to molar flow rate of the N. The reflux ratio is 3. 8th stage including total where the reflux ratio is given. Feed entered at the 4th stage of the column. 3rd stage. So you are saying pressure value is not given. That's the issue. No, it's atmospheric, right? So, extractive distillation column at atmosphere. So you have this data also. So your condenser pressure here you have to write it 1. Rest of these are the optional. See here the total first value is compulsory because the condenser will maintain your overall pressure of your column. Okay, while the second data, the stage 2 or pressure drop, these are the optional. So if you will not provide it, it will consider it as an ideal, and without it will consider no pressure drop across the column. Okay.
Okay, sir. Thank you.
Yeah, welcome. So coming back to our problem again. Just a minute, guys. Can you just hold for a moment? I just have to do one task. Yeah, sorry. So coming back to our problem, here we just wanted to see how this separation has worked out. So go to the stream result part at the bottom, result summary and streams. So this is the complete data here given. So first let's look at the what is happening at each individual block and where the separation is happening. So we have our feed F, which is fed to C1. From C1 we get a D1 and bottom product B1, right? So let's look at the mass flow rate. We said that the lighter key component in the C1 is this IC4, NC4. So all the components above the NC4 should be part of distillate. That can be seen here also, and you can see from the flow rate most of the component went there, and rest of the IC5 to NC6 should go into bottom part. Okay, that is also being seen. So that's how the separation of NC4 to lighter component has happened into C1. Then from there it went to C2 column, where you have D2 and B2. Okay, so C1 column is this. So from top distillate went to CR1. Okay, so let's look at for CR1. CR1 has DR1 and BR1. So in the DR1 and BR1, so what we expect from here, that the C4th component, okay, IC4 and NC4 should come down in the bottom part. So from the flow rate you can see that majority of D1. So majority of IC4 and NC4 came to the BR1, bottom product of the first red flag column, while the light key component went into the distillate part. This bottom product of red flag went to C2, where N-butane and isobutane has been separated. Okay, so if you will see, feed will be BR1 and D2 and B2. So from here the main IC4 and NC4 stream is going into C2 column, where IC4 and NC4 separation should occur. So bottom product of distillation 2 unit contains major amount of N-butane, while the top product contains major amount of isobutane, while some amount of other C2 and C3 component. Okay, in the CR1 what should happen? You have lighter components, methane, ethane and propane. Okay, that should be separated in this CR2 column. So if we will look that, let's select DR1 and output will be DR2 and BR2. So what is happening here, that you have majority of C2, C3 components. Okay, sorry, we don't have C1 here. So the separation of C2 and C3 should happen in the second red flag column. That is also happening, that you have in the bottom part you have majority of C3 and the top part you have majority of C2. Okay, so we separated C2, C3 here, iso and normal butane into this column. Now we have this, from the first column you have IC5, NC5 and NC6 coming to the C3 column. Okay, there the separation of IC5, isopentane and N-pentane should happen. So first outlet of B1 is going to C3, where we have outlet stream D3, B3. So you can see you have majority of IC5, NC5 and NC6 coming, which are separated. So mainly NC5 and NC6, that will be heavier component compared to the isopentane, right? So they are going into the bottom product, while top has mainly isopentane and some of the lighter components. some NC5 went into that because that is a separation efficiency point. We can change the distillation column parameter to increase or decrease the fraction. Okay, so this is how the separation of C2 to C6 component has happened. In the B3 part, you had IC normal pentane as well as normal hexane. So we can further use any distillation column to separate that also. Okay, so this is how the separation process of this hydrocarbon mixture is coming. Now, third example that we have discussed, but actually we are running out of time, so maybe should I complete it today or should I keep it for the next time? What you guys want to do? It will take 10 to 15 minutes more. I mean, we still have 10 minutes for our lecture. Yeah. So it's a relatively simple example. So let's try to finish it today. What I will do, I will just directly open the preloaded simulation. Okay. So this is case study 3 for the, yeah. I don't want to save this simulation. Let's go. So you have been, so here the mixture is ethyl acetate and acetone, and the solvent is water. So what do you think? Water will separate whom from whom? As in, it will have affinity towards acetone or ethyl acetate? Can you guess? Water is used for separation of mixture of acetone and ethyl acetate. So your extract will contain water as well as majority of acetone or ethyl acetate. Do you know? It's not opening. Think about it. If I compare ethyl acetate and acetone, can you guess, like water should have affinity towards acetone more, right? You might have heard the mixture of acetone and water. We haven't heard mixture of water and ethyl acetate. So water is used to separate acetone from this mixture. So acetone has an affinity towards the water rather than the ethyl acetate. So acetone will be our will be part of the extract, while the raffinate part will contain mainly ethyl acetate, some amount of water and acetone. Okay, so this is how the if I want to put it in the extraction term. It's not recording. Just give me a minute. It's just not responding. Anyway, we are at the end of the session, so maybe next time I can take this problem. So what I will do, on the start of the next class, we will solve this problem first. Again, it's a very straightforward problem. Once that is completed, then we will move ahead with the another example. So the question 4 also I had taken for this week's class. So this is again the same kind of azeotropic distillation kind of a separation. So here you have a mixture of water acetone, and this EIPK is used as an solvent which is fed to the flash tank to separate out the two liquid phases, and then further extraction process has been done. Okay, so this two example we will stop it here. We will take it from the next class, right? And then again I have planned another example. So this LHHWV kinetics, that I had already done one example for that, but probably I will pick out another example, so that will be related to your week 11's assignment also. So probably that should help you to do the assignment of week 11. Okay, so for today's class I will stop it here. Anyway, this is not opening, so we will start with question number 3 from next class onwards. Okay, I'm stopping the recording. Do you have any doubts, Rishikesh? Okay, so yeah, I'm stopping the recording. You can leave now. Yeah, thank you.